So here's what we're covering today. We're going to start out with GM regulated voltage control, or RVC is the term for it. That also includes, and you'll see it, SARVC, which stands for standalone regulated voltage control, typically used in trucks. Then we'll go through the Ford Smart Charge system, which is the most common system. Ford has a couple of them out there, but that's their most common system. And then we'll go through how the Hyundai Alternator Management System, or AMS system, operates. When we complete that, we'll go out to the shop. I've got a Hyundai out there that we've got an oscilloscope set up to and a scan tool set up with, if you guys don't get the opportunity to play with those tools. So, computer-controlled charging. I don't know how much of this you guys get faced with, but what are the benefits of it? This is an overview of the whole thing. Improved fuel economy, you know that's the biggest deal to an OE, right? Anything that improves fuel economy makes them happy. Improved performance, stability, you know, you can read through the list. Really, increased battery life is my favorite. I don't know about you guys' market, obviously. I live in Oklahoma, center of this country. You know, that's about where I go. But I can tell you in my market, battery life 5 years ago was about 3 years. That's about all you get out of a battery. I have an 05 Mustang sitting in my driveway that has the original battery in it because it has a Ford Smart Charge on it. It's one of the big benefits to computer control is we don't overcharge the battery constantly. But better lamp accuracy, fail-safe charging is important for all of them. Idle stability in small engines, you know, matters a lot. Those are the basic benefits. How does it work? Just a big picture overview. The computers, modules, whatever's in control establishes the voltage set point for the alternator. The battery state of charge and vehicle conditions are always monitored, which includes stuff like windshield wipers, headlights, you know, anything that adds load to the car. The voltage based on those conditions, and it varies anywhere from 11 to 15.5 volts, which causes us a lot of grief when customers see 11 volts coming out of their car. They think it's broken, right? It's not a typical charging system. Some of the common features. Softstart, you've probably been exposed to this somewhere. The graph on the bottom is from a GM system. This graph represents vehicle startup time. This is where the crank started. And then we started it up and we slowly added loads to the car. The text up there says something like 3 to 10 seconds. This is to allow for quick startup, right? An alternator is somewhere in the neighborhood of 5 to 10 horsepower depending on the application. So we shut that thing off during the crank cycle and then we slowly apply that load once the vehicle starts to help idle stability. And I make fun of it. They made reference earlier to my Ford background. I make fun of this because I have a Ford drivability background. Ford idle air control, if you've ever done drivability kind of work, is a joke. They never could maintain idle. It was a big issue for them. So this is one of the ways they've got better control of that is by bringing the alternator on slowly to keep that load off the crankshaft. And I've got a couple of notes, I guess, and I have to remind myself that I'm teaching 3 classes at once here. For General Motors and Hyundai, this is built into the regulator. For Ford systems, it's commanded by the module. It's a little different for them. Load response control, the other common feature to all of them. This is, you know, if you live, depending on where you live is where I make the joke about this one. For me, I drive an old Ford truck that's a mutter with fog lights all over the top. When you flip all those things on, you're asking for 120 amps. Or if you're a 16-year-old kid, you're flipping on the subwoofers in the trunk. If you suddenly ask for 150 amps, you know, you're asking for another 5 or 8 horsepower from the engine. If you're asking that out of a little 4-cylinder, what happens to idle? Does that and has to respond, right? So that's the reason for load response control. That's what this graph is attempting to show you. This is the FR circuit or feedback. Somebody asked for a lot of load right here at this point, and it took the time to add the load on slowly. It's a rate based on engine RPM, 2 to 10 seconds, depending upon how much load you're asking for and what engine RPM is. Becomes inactive somewhere around the 3,000 RPM mark. RPM is engine RPM. I don't, you know, the terms you guys use. G would be generator RPM for alternator speed.
So in the meantime, you feed it out of the battery?
That's correct.
Why does the charge light not come on?
It's because the PCM is in control of the charge light.
Okay.
And we're going to see some samples of that, how it's different between the different manufacturers. Lamp can still, for GM and Hyundai, we'll see that lamp can still be controlled by the alternator like we're used to, right? No charge, ground that circuit kind of an idea. But for most of them now, the charge lamp is controlled in a bigger picture, done by the PCM. And so it sees, because they have a fail-safe mode, they'll still charge even when you unplug them. So you don't want to turn a lamp on. You may want to turn a lamp on in that condition, but without a typical lamp circuit, you wouldn't be able to do that. Limp modes. So these get a little bit unique by the manufacturer. You know, if something goes wrong, we're going to charge something. I mean, it's basically all it amounts to. GM and Ford fall into this 13.8 range. And that's typical of all manufacturers for a default charge range. The exception to that in this case is Hyundai. They call it normal mode or AB normal mode. I just refer to it as AB normal mode. And it charges at 14.5. But for Hyundai, this isn't just a fail-safe. This is a used strategy all the time. If it's under heavy load, and we'll see this, it'll just command it to go into this mode. But GM and Ford, it's simply, if you unplug the regulator, start the car up and rev it up, it'll fall into this default mode and charge at 13.8. The PCM will turn the charge light on at that point. So now, going into one specific system, the GM system, there's two of them out there, RVC and standalone RVC. So standalone is most trucks and SUVs, not all of them, but most of them. And it's got a 7-wire battery current sensor. So we won't talk about this one directly since I've consolidated classes. It kind of hurts us in a time frame issue. But this system and this system operate the same. It's simply what's controlling the alternator is the really smart battery sensor, right? But we'll discuss it in this term. So the way the GM works, the communication circuits. So the top one's talking about, and I know these graphs are a little hard to see, they're red on the oscilloscopes, but the L circuit, what we know as an L, a lamp circuit, is a 5 volt, 128 megahertz signal, variable duty cycle, that commands the charge rate. Now with GM, what is a little unique about it, going back to the lamp question, is when you first key on, you start the car up, it sends out its lamp circuit signal as this duty cycle, but the alternator will ground it just like it did a lamp circuit. So if you're back probing that wire, as a technician watching that wire, you see it go to 0. You don't see the duty cycle because the alternator's not charging, so it treats it just like a regular lamp wire in that regard. The PCM sees it, pull that circuit low, turns the lamp on. The output, the FR circuit, 12 volt, 400 megahertz, give or take, and it's a direct feedback. It's actually directly what the regulator's doing, right? The toggling of the regulator on and off, that's directly what you're seeing is the output of that on the FR side. The PCM monitors that to verify alternator operation, but it also uses it to determine I need to charge more, I need to charge harder, or it uses it as a determination as load ramps up, I need to increase the idle air control time or bring up the idle RPM to prepare for that surge we were talking about. So specific to them, L circuit duty cycles, and I have this gauge up here, and we're going to talk about the modes GM operates in. This is a normal operating range. So I don't know what you guys are accustomed to. I'm a car guy, right? And we're all car guys. That's why we're in the automotive industry. I like a real voltmeter. GM uses a real voltmeter. It's terrible for customers. Customers got no business knowing what's going on. Because when this happens, they think something's wrong with their car, right? Right? And Ford, and as much as my background is Ford, I hate to say it, their gauges are just dummy lights, right? They just stick it up there in the middle somewhere and go, that's good. But GM still gives us a real voltmeter, and it does cause us a lot of grief. The tech line takes calls on that quite frequently. Gives you an idea of the range of duty cycle commands. It commands anywhere from 11 volts to 15.5. Numbers outside those duty cycles indicate either short to ground or short to power, right? Fail-safe, or fault. You'll set a code for either one of those going outside of that duty cycle. So how does it work? Kind of a big picture version of this. And as I said, the SARVC is kind of the same way. It's just the body control module and PCM talk to the battery sensor, and the battery sensor talks to the alternator, but the operation is still the same. So when you first key on, they call it precision voltage lines. I like that they call it precision. It's just volt lines, right? The BCM sees battery voltage. It takes a look at current going into or out of the battery. In this case, we're key on, so it would be out of the battery. It uses the intake air temperature from the PCM to guess at battery temperature. Now, as these systems progress, we're seeing battery temperature sensors being added to the battery sensor, or to the current sensor. But typically in the earlier versions, it's all intake air temperature is used to guess at it. So the body control module uses this little lookup table to decide what the battery state of charge is. And it uses that information based and loads. The BCM for General Motors is watching windshield wipers, watching headlights, all those other electrical loads. So it combines all that information to decide a command for the alternator. In this case, just talking generically, let's just call it 14 volts. So it says, PCM, I need you to turn that on at 14 volts. The PCM has the chance to change that based on load. You got your foot stuck in the throttle, something like that, the PCM can change it. But generically speaking, that command just simply passes through. The PCM converts it over to that 5 volt signal we were talking about, and it tells the alternator over the L circuit, I want you to charge at 14 volts. Pretty simple, really, right? See, it's kind of large for just an alternator. Then the feedback goes back to the PCM telling it how hard am I working to do that job. Literally what the regulator's doing to the rotor. So that kind of makes it the full circle. Now I add to this and I say, if you have corrosion in the B+, And I would say this is probably the largest cause of repeat failure we see out in the field, is this very issue right here. So if we lost a volt between here and here, the BCM said, I want 14 volts. The alternator made 14 volts, but only 13 made it back to the battery, just arbitrarily making up the numbers. So the BCM's watching that. It sees 13 volts and it says, whoa, I wanted more than that. So the BCM sends a new command, right? Those precision voltage sense lines. So it sends a new command to the PCM. It says, hey, I need another volt out of you. The PCM says, no problem. I'll tell the alternator to give me another volt. Now the alternator's making 15 volts. And how much is getting to the battery? 14, just what we wanted. So now the BCM's happy, but what's the alternator doing? It's overcharging. What happens to it? Gets hotter. Then what happens to it? It dies, right? In some way, shape, or form, it dies. So that's where we misdiagnose these cars in the field all the time, because we're performing our diagnosis here, typically. So a technician comes in with a legitimate alternator failure, orders up a new REMI unit, sticks it on the car. He's got his voltmeter out here, fires the car up, he sees 14 volts. It's working beautiful, isn't it? Ship it, that car's fixed. That customer's back in 30 days, 60 days, 120 days, whatever it is, with another burned up alternator. And what does the technician say? That REMI alternator is a piece of junk. Burned up 2 of them in the last 6 months. No, it's not. You failed to prove out diagnosis. You went here and you didn't come back here. This is the most common source of problem we see in the field. It's a big picture, though, of how the GM works. Does that make sense to everybody? Okay. And most of that's covered in the GM book that I gave you. The interesting thing, these books were written over different generations. That GM book kind of covers it by application, right? It covers a pre-RVC car, a PCM lamp-controlled car, then it covers an RVC car, then it covers an SARVC car. So you can kind of get a sample of each one of those progressions of this system through its life. So here's the fun part to me of GM. They use up to 9 different operating modes. The inputs it used to determine what are listed here, and I'm not going to read through all these, they basically come down to what's the condition of the battery, the condition of the alternator, the load on the engine, right, and the battery temperature in SARVC, where they moved a sensor out there. So that's just a list of all the potential inputs they use to make a decision on modes of operation. The different modes listed here, there's up to 9 of them. Not every car has all 9. It could have any combination of these depending on how it's programmed. SARVC is actually the one most likely to include all 9. Now we'll kind of go through these individually, but again, our gauge looks like that guy right there. And these are all listed in your books as well. So some of these get pretty in-depth in text. I won't read them to you, I'll just hit the big picture. Right after you start it up, you need to charge back, right? That starter demanded 120 amps. I hit the battery pretty hard. I got to put something back in it. So for the first 30 seconds, we're going to go to 14.3 volts. Reclaim some charge into the battery. Once you're running charge mode, and this is the one you want to be in when you're diagnosing the car. So what I tell technicians, and they list the items here, right, to fall into this mode. The battery state of charge is low. Any of these things are turned on. Temperatures are right. These are all in your books. It would bore you to death if I read them. But basically what I tell a technician, because there's 9 different modes and you don't know which ones you have, turn on the windshield wipers, turn on the headlights, turn on the rear defogger. Load the car down hard. If you load the car down hard, you will fall into this mode. Then you begin your diagnosis of the charging system.
How do you get the SOC to less than 80%?
You don't. But when you demand windshield wipers on, you pull 30 amps, 20 to 30 amps potentially through the wipers, another 10 or 15 in the rear defogger. You get that much current flow going, it makes battery voltage dip, and so it's interpreted as low state of charge, even though it's really not, but it gets interpreted that way because of the voltage dip. So that's the quick way to force it into your diagnostic portion of things. Fuel economy mode is my absolute favorite. This is the one that causes us the most grief. We take calls on this all the time. You'd be amazed because it does this to the voltmeter. Fuel economy mode, when you meet all these conditions, and again, I won't read through them all, they're all in the book. When you meet all these conditions, you fall into this fuel economy mode. It's easier to get into than you think. You get up on the highway, set the cruise control, you're riding into Indianapolis, you might likely fall into this fuel economy mode. So what happens for us out in the field is the customer got a new alternator last week. Now they're driving down the road and their volt gauge does this. And they call the mechanic back and they say, look, you put a new alternator on my car, it's not working. And the mechanic tries to explain to him, no, this is a fuel economy mode you're falling into. And the customer says, and I promise you this is the way it works, I've owned this car since it was brand new, it's never done that. You don't know how many times I've heard that. Well, the truth is, when that customer bought that car brand new, they never looked at the voltmeter. The stereo was going, they were playing with the buttons, they got a brand new car, they're having a good time. But now you bolted an alternator on it yesterday, so they're driving down the road staring at the voltmeter, aren't they? Right? They're just waiting for something to go wrong. So it did this the whole life of the car, they just never knew it. And I promise you, now that I've told you that, I've cursed it to happen to you too. You will take a phone call from somebody you know, and they're going to be in this mode. It's going to happen. Right? The quick way out of it, you know what the customers say is I cycle the key and it goes away? But remember, you go into startup mode then, right? Where you're back at 14.3 volts. The other one that's a real voltage reduction is called voltage reduction mode. And again, a different set of requirements. And what I find interesting about this, and GM to me is so interesting for this reason, is how complicated they make some of this. The targeted voltage set point is 87% of charge mode set point to a maximum of 12.9. That just seems overcomplicated to me, right? Why not just say, let's make it 11 volts, let's make it 11.5 volts. And I thought about this a long time when I started teaching this because of all these different modes. You know, we're up to almost a mile a gallon improvement in fuel economy based on how we're controlling the alternator. That's why it's so complex. That's why it's all this stuff instead of just being fixed values, because they're pushing for everything they can get out of this thing. But this is another voltage reduction mode. The problem is if you're in either one of those, particularly fuel economy mode, for any length of time, you go into this one, battery sulfation mode. So, you know, ideally, if you can hold the battery in the 90% state of charge, 95% state of charge, that's the ideal place for a battery to live the longest life it can live, right? Don't push it to the limit, keep it right under that. So we were driving down the road a minute ago in fuel economy mode, right? So if you're in that mode for 45 minutes, it goes to this mode. Now it's at 15 volts, 15.5 volts. So now the customer who's driving along like this, watching that gauge down here going, oh God, I hope I make it home. Now suddenly the voltmeter goes, bam. Now they're really convinced their car's broken, aren't they? Because I went from not charging to overcharging. But it doesn't stay in this mode very long. It says up here somewhere, up to 3 minutes. So it's just meant to clean the plates, right? If you keep a battery too low too long, you sulfate the plates. The way around that, hammer a lot of voltage to it, spike it hard, you clean off the plates, and then you'll send it back into a regular mode again. So now the customer's watching this. Now you see why I say customers shouldn't have voltmeters, right? There's too much going on for them. There really is. Headlamp mode, and again, not every car has every mode. Flip on the headlamps, you force it into charge. It ramps it up to 14.5. Hopefully the car has that, so when you want to diagnose the car, all you get to do is flip the headlights on, you force it into charge mode, where you're up there, you're moving some amperage, moving some voltage for diagnosis. Fuel pump boost mode, I make fun of this one when I teach. I'm from Oklahoma. I don't know if you guys have ever been around Oklahoma. My state is flat. There's nothing. Wheat fields, that's what we have. Every road is square, and we have wheat fields. So now you're driving down the road, and because we're long and flat, you're in fuel economy mode all the time, and then a tractor pulls out in front of you. There's my joke. We're farmers. You stand in the throttle. If it sees you stand in the throttle, because I'm going to go around this tractor, it bases it on, I opened the throttle up, I'm going to bring the voltage up a little more to get a little more fuel pressure, and then once I see fuel flow, and it actually, instead of basing it on throttle, bases it on fuel flow. I stood in the throttle, I jumped the voltage, I passed the tractor, I backed out of the throttle, the PCM sees fuel flow fall below 5K grams per second, then it goes out of this mode. So this is another one of those, now it's responding to my foot, right, if the customer's staring at the gauge. De-ice mode, this is turn on the rear defogger, it's cold outside, we're going to bump voltage up. Again, still meets all the same kind of criteria. Targeted voltage somewhere between 14, right at 14 and 15.5, depending on conditions. Windshield wiper boost mode is the same thing. It's just a different load. So the reason for having the different ones, headlight, wiper, not all cars use each one. Again, maybe all of them. This is another one of those, brings it up to 14.5. And that's the end of that one. So it's back to this original. So there's the 9 modes again. GM is the only one that does this with so many modes of operation. It's kind of unique in that regard. So diagnosing this system, RVC, SARVC. Condition and state of the battery. I can never beat this up enough for everybody. Battery state of charge, the battery condition is everything. But verify mechanical systems, alternator operation, and diagnosing by trouble code, which truly, this is a real good pointer for where you want to go diagnose, but really completely unnecessary when we get to the end of this program. So battery state of charge, I just beat this up over and over and over. Battery is always guilty until you prove it's innocent. It doesn't matter whether it looks like this one or whether it looks like this one. It's bad until you prove it's good. If you've never been bit on the butt by a battery, you've not been working on cars, right? Everybody gets bit by, it's the simple stuff that we miss, right? I personally have been through this where I took the alternator off my own Mustang, my old Mustang, and rebuilt it because the battery wasn't even 30 days old. Looked like it wasn't charging because it had a shorted battery. I refused to believe that brand new battery was going to be bad. Took the alternator off, rebuilt it, put it back on, had the same problem. It's one of those stupid mistakes that everybody makes. So I just beat that up over and over in every class I ever teach. But before you begin any diagnosis, you got to be at least at 12.4 volts, right? And that's still at a 75% state of charge on a battery, 12.4. Accessory drive stuff. So I've got a little bit of a presentation that goes with this where we talk about belts, pulleys. I don't know, I expect you guys use a lot of the clutch pulleys. Have you guys had experience with clutch pulleys? Because this is everywhere for us now and just beginning to really dominate the market. We started out talking about belts, mainly because I'm old, is the reason I put this in here. Neoprene belts are what I'm used to. You knew when they went bad. They had chunks gone out of them, they glazed, they squealed, they made all kinds of noise. You knew when they were bad. Newer belts, referred to as EPDM belts, big long name, they don't make noise. They don't squeal, they don't squall, they wear out like a car tire does. So it makes missing diagnosis on these is actually pretty common. In fact, last week, I work out of the Edmond facility in the Edmond Engineering Lab. I helped an engineer go out and diagnose his truck that had a problem. It was this guy right here, and he missed it, totally missed it. The only way, and here's a picture of how they wear, right? They normally start out with a V profile. As they wear out, they just become a U, so they go to the depth of the pulley, right? But they don't make any noise when that happens, so that's the big change. There's a couple of tools. These are free from the manufacturers of belts. Dayco makes this one. You just stick it in the groove, put a flashlight behind it, look for light, right, to determine if the belt's good or bad. There really is no other accurate way to tell. Now, you can, if I back up, they kind of glaze over as they start dragging the depth of the pulley, so you kind of get some clues. The pulley itself, the top of the V of the pulley, will get real polished when it hits the bottom. So there's a couple clues, but you don't get it in traditional fashion of noise. Belts and tensioners, I don't really talk a whole lot about these, right? They got to work good. The spring tension's got to be smooth and operate. If it isn't smooth and operate, put on a new one. I kind of give guys, and I'm not one to throw parts at a car, but I kind of give a general rule of thumb. If this guy's bad, replace all the idlers, replace all the small pulleys too, right? Because those things are spinning their tail off. The pulleys themselves, you know, we started out V-belts. These still exist. There's still tractors out there, not a lot of them. We went to serpentine belts, still cut and dried kind of stuff. We first started seeing these. The first ones I remember as a technician were on Chryslers, were the first ones to introduce these. The overrunning alternator pulley, which was just a one-way, and then the Leighton's OAD, which is a decoupler pulley. So the one-way itself, it was simply, you know, these two are just support bearings, and the one-way's in the middle. It was just meant to let the rotor run free, right? So this was, you got your foot buried in it during a 1-2 shift, RPM falls down quick, lets the alternator run away a little bit. Shut the car off, lets the alternator run away a little bit. The rotor of the alternator, if we're talking about the FED, front engine accessory drive, for me, for a field guy, the alternator is everything. It's the heaviest component out there. It's a magnetic field and a big heavy rotor gives us a lot of grief. These fail, every one of them, seems like. If you had any experience with Chrysler, they all failed, every one of them. But then we went to this OAD, made by Leighton's. It says it has a one-way clutch and a torsion spring. It really doesn't have a one-way. It does freewheel, but it doesn't really have a one-way. We'll see a picture of that. It absorbs energy. So I don't know if you guys deal with this, but it's tuned to the firing frequency of that engine. So firing frequency is RPM times half the number of cylinders. Wherever that frequency is at a given RPM, where it spends most of its life, that's where they tune that spring. Parts and pieces that make it up. So bearing in the back, really no big deal. So the belt's driving the pulley. Pulley's grabbing this washer. Washer's grabbing the clutch. So now the pulley's grabbing the clutch catches the edge of that spring. The opposite edge of that spring is tied to the rotor or the shaft or the big spinny part in the middle. And that's the weight. So the spring winds up until it hits this clutch surface, locks up, now the rotor's turning, right, with the belt. So that's the one-way effect is when you have a sudden deceleration in engine RPM, the spring unwinds and it just gets to freewheel. There's really no one-way there anymore. And I'll throw in here too, because this is something to be proud of as a RIMI employee, is in our reman process, we are the only authorized rebuilder from Lightens, but when we rebuild, we have to replace everything. We get to reuse, you know, the big dumb parts. We don't get to reuse any of this kind of stuff, right, the wear items. So, but every unit we make, every reman unit that goes out, either has a new one or a reman one on it. We don't ever reuse them. We don't sub them. We've got competition out there who, because the cost of this pulley is so high, they put a different pulley in there that they make you think is a Lightens pulley. And I've taken some of these apart down in engineering. Some of them are three fingers with rubber in between them. Right? There's no torsion to that. It just catches a bump, right? But that's how we get beat down in the competition. Because we're selling to whoever we're selling to, and then they come in and say, well, we'll sell it to you for cheaper than that, but they're not using a Lightens pulley. We don't sub for this, we don't fake this, we do this right. It is something I'm pretty proud of, that we don't compromise in quality when it comes to this kind of stuff. All right, so I was still in the middle of RVC, and I jumped into the pulleys. So now I came back to the code list for this car in diagnosis. So the code list sitting here, the most common ones you see for GM are the 621, 622. Typically, you'll set one of these two codes and a different code. Now, not all cars have all codes. You know, I mean, this is kind of a generic pull from when I set up the class. But for GM, what you normally get is a 621, 622, accompanied by another code. So really diagnosing it, this is L circuit diagnosis. And I teach this a couple of ways here because technicians, and you know, the first question I ask field technicians are, when was the last time you measured duty cycle? And the room gets really quiet. Nobody measures duty cycle anymore. Back in the day, and I just marked my age, you had to measure duty cycle to measure carburetors because the solenoids were commanded by duty cycle. There was a lot of that we had to measure that way. In today's day, nobody turns their meter to duty cycle anymore. So I also give them voltage, right? Because does this tell you exactly what's being communicated? No. But do I care? No, I don't. All I care is that it's happening. And that's the way I teach this for all the guys. So in the GM L terminal, the PCM's command of voltage set point, key on, engine off, it shows a 0% duty cycle, 0 volts. That's because it still operates like a traditional lamp, key on, engine off. You flip the key on, the PCM indeed sent down a 5 volt, 128 megahertz duty cycle signal, and the alternator saw that, turned on, looked at itself and said, I'm not charging, I'm going to ground that wire, just like it would any lamp circuit. So that's the reason it's at 0 now. If you unplugged the connector and checked it, you would see the L signal coming down that wire. Okay, once you start it up under a low load condition, and these are just sample numbers that we've pulled from cars, not any fixed number, but you're at a low load, about a little over 3.5 volts, 70% duty cycle. As you add loads to the car, the values are going to go up. It really is that cut and dried. And it's true of all of these applications we're going to look at. So when the technicians pull those codes that said, 621, I got an L circuit failure, and they go into a panic about, is the PCM communicating, is it not communicating? It's as simple as back probing the wire, add load to the car, start it up, add load, see if it responds. This tells me that it is responding. The PCM is making a command, the alternator's getting it. The F circuit, which is the feedback, FR, key on, engine off, and this value, I've always told and referred to this as preloading of the rotor. When it saw an L circuit command come down, it turned itself on, it sent a little bit of magnetic field through the rotor to kind of get it ready to go. So that's what you're looking at here. But once you start it up under low load conditions, and as you added load to it, the values went up. And we saw earlier that duty cycle chart that showed you inputs, and then this is a direct reflection of how hard the rotor's working, right? This was looking at exactly what the rotor's commanding, or the regulator's commanding. Questions about those two? Because fixing a GM RVC comes down to those two screens. It is really that simple. So there is one shortcut for GM, and I always try to give a guy a shortcut. and it's for the F circuit. So alternator unplugged, using a scan tool, and this is the Solus Pro, this is kind of an old one. You pull up the generator F terminal and it shows 0%. F terminal is feedback, right, from what the alternator's doing. It shows 0% because, well, it's unplugged. Then if you take a fused jumper, and it's only fused to protect you, jump 12 volts into that wire, but the PID immediately jumped to 100% value because you sent voltage back up to the PCM. So that diagnosis from this point all the way through the PCM, did the PCM read the alternator correctly? And finally, it kind of closes out with an alternator amperage test. And I always bring these up at the end of each section. Don't spend a lot of time on them, but you know, they're cut and dried. If you're using a manual tester, you rev the engine up, you load it down till the alternator sees about 13.8, take an amperage reading, you ought to be more than 80% of manufacturer specification.
Back to your previous screen.
Yes, sir.
If we were using that to find if the trouble was in the wire, would it blow that fuse if it was grounded in there? And
If the wire,
there was a short somewhere?
if the wire was shorted to ground, yes, it would blow the fuse. That's why I said it's meant to protect you. Yeah. If the wire's open, the PID won't change. It'll remain at 0. If the wire's shorted to ground, fuse blows, PID remains at 0.
That'd be a quick way to tell if your wire was compromised. Just watch see the fuse bleed.
It absolutely is. Now, the only, from a technician point of view, my only complaint with this is I only get to deal with the F circuit. I cannot deal with the L circuit this way. Because for GM, and we're going to see as we move into some of the other makers how they work. For GM, this is all generated at the PCM, right? The 5 volt, 128 megahertz variable duty cycle signal coming out the L circuit from the PCM. So you can't manipulate that and then watch a PID value. The amperage test, the value is just to protect capacity. And I go back to the number of years I've spun a wrench. There were a lot of years where factory shop manuals said you could take a voltmeter at the battery and fully diagnose the charging system. You did not need to check amperage. That's not really true, especially in today's capacity, where there's 6 phases in where there's 2 stators shoved inside one alternator, basically, where you can get lots of capacity and you'll still fall out one leg of a stator, but you'll still pass a voltage test, but you won't pass an amperage test. And we'll talk more specifically about that with Ford because there's some Ford examples that work really well for that. Here's our favorite. So when I started out talking about GM, I was talking about how there's voltage drop in the B+ is our #1 concern. This is the way we address it. So it's kind of a short, quick way to do it. Engine running, loads on, preferably everything turned on. You want the alternator moving as much amperage as possible. Both leads of my voltmeter at the battery, moving both leads of my voltmeter to the alternator, ground to the housing, red to the back. You have to be within half a volt on these 2 readings. This is required, and I always use the word required, anytime you replace an alternator, because this is the problem that causes repeat failure. So if you see more than half a volt difference here, how would I isolate it? Anybody done this before? So if I've got more than half a volt difference here, what circuits have a problem?
Probably the ground circuit.
Might be the ground circuit, might be this one, right? Got to be one of the 2. Right, in this example, especially drawn this way, absolutely the ground's where it's going to be, right, drawn this way. So individual tests. So if this reading, backing up, if these readings are more than half a volt apart, then you check them individually. Same conditions, engine running, loads on, repair the side with the highest voltage drop. You can never have more than half a volt. If you read manufacturers' manuals, they move this number anywhere from, I've seen as low as 0.1 to as high as 0.8. It doesn't really work to have this huge range of specification. If you take 0.5 as a good rule of thumb for light duty, it works all the time. So here I'm measuring from positive to positive. Under those conditions, I got 0.2 of a volt drop. Over there I'm doing the ground circuit, right? Negative terminal of the battery, housing of the alternator. I got half a volt up there. I have a ground problem. Where can it be? It could be right here. It could be this cable. It could be this mounting surface, or very commonly where the alternator is mounted into the block, especially in an environment like this where they use salt on the roads. This becomes a lot bigger issue.